students, welcome to Sunil's tutorial. I'm Sunil Mirwani and today we'll be doing this chapter called as oscillation. Now let's try to understand an angular SHM. Let's try to understand angular SHM. Now there are a number of examples where in which different particles of a body oscillate along a curved path. Now let's see the oscillation of a body. So far we were considering linear SHM. Now let us try to consider a curved SHM, right? So I can say there are a number of examples. There are a number of examples in which different particles of a body oscillate along curved paths. So when a body, instead of oscillating on a straight line, oscillates along a curved path, then that body is said to perform an angular SHM. Instead of linear SHM, the body is said to perform angular SHM. In linear SHM, the body moves along a line. In angular SHM, the body moves along a curved path, right? So I can say in such a case, the body is said to perform angular SHM. Right? Now, when a small angular displacement is given to a freely suspended body, then it performs an angular SHM. When a small displacement is given to a freely suspended body, it begins to perform an angular SHM. Right? Now, if it is moving in angular path, then the force is going to be an angular force, and we already know that angular force is called as torque. So the torque acts on the body which is displaced and tries to bring the body back to its mean position. I can say that the torque acts on the body in the displaced position, and tends to restore the body back to the mean position back to original position. So the torque is going to try to bring the body back to the original position. Therefore, I can say that the torque can be called as restoring torque, as it is trying to bring the body back to original position. I can say that this torque is therefore called the restoring torque. Is called as restoring torque, and it is first directly proportional to the angular displacement. More the angular displacement, more will be the torque that will try to bring it back to its mean position. Is directly proportional to angular displacement. Directly proportional to angular displacement. Theta, right? And second is in the direction opposite to that of angular displacement. The angular displacement and the torque are in opposite direction, and is opposite to the direction of angular displacement. Right? Therefore, I can say that torque is going to be minus mu times theta, where I can say mu is a constant whose magnitude is equal to torque per unit angular displacement. Mu is a constant whose magnitude is equal to torque per unit this angular displacement. Right? The negative sign here indicates that the torque and the angular displacement are in opposite direction. Fine, we'll get this thing here. Now, let's see this. Now let's consider the differential equation for a linear SHM. The differential equation of linear SHM. The differential equation of linear SHM is m times, we've derived this guys, d square x upon dt square plus kx is equal to 0. This is my differential equation for linear SHM, where m is the mass in linear motion and which corresponds to the m is the mass in linear motion, and the mass in linear motion corresponds to the moment of inertia in rotational motion. Moment of inertia in rotational motion. I. So m corresponds to I. What is m for linear motion is I for rotational motion. Similarly, I can say that d square x by dt square corresponds to angular. This is my linear acceleration, which is linear acceleration, corresponds to angular acceleration, that is d square theta by dt square. Right? Now, similarly, k, which in linear motion corresponds to torque per unit, k of linear motion corresponds to mu of angular motion. If I substitute these values, I will get, therefore, substitute in equation of linear motion, If I substitute in equation of linear motion, I will get I d square theta by dt square plus mu x or mu theta is equal to 0. So this is going to be my differential equation for angular SHM, right? This is the differential equation of angular SHM, right? Once you have the differential equation for angular SHM, I can also say that d square theta upon dt square is minus mu theta upon I. So that will be minus mu upon I theta, right? In this case, I can say mu and I are constants. Moment of inertia, that's the mass of the body in rotational motion. Mu is, we've already said that mu is proportional to the angular displacement, right? So in that case, I can say here mu and I are constants. Therefore, I can say that the angular acceleration of a body in SHM, I can say therefore angular acceleration, the angular acceleration is 1 directly proportional to the angular displacement theta, directly proportional to angular displacement, and second is the negative sign indicates that it is in opposite direction. That means the angular displacement and angular acceleration are in opposite direction, and its direction is opposite to that of angular displacement. Right? So on the basis of this, now I can define an angular SHM. Definition. How do I define an angular SHM? An angular SHM is defined as an oscillatory motion of a body. It is the oscillatory motion of a body in which the torque is directly proportional, to the angular displacement. Torque is directly proportional to the angular displacement, and its direction is opposite to that of angular displacement. And its direction is opposite to that of angular displacement. That's how I define an angular SHM. Fine, do we get this thing here? Now, for a linear SHM, we had said that time period T is given by the formula 2 pi upon square root of linear acceleration per unit linear displacement. That was my time period of a linear SHM. So if I use similarly, I can say that if I use the same analogy, I can say similarly for angular SHM, time period T will be equal to 2 pi upon square root of instead of linear acceleration, it will be angular acceleration per unit angular displacement. Right? That is going to be my time period of an angular SHM. So do you understand what is an angular SHM? It is an oscillatory motion of the body in which torque is directly proportional to the angular displacement and is in the direction opposite to that of angular displacement. Next, let's see a magnet vibrating in a uniform magnetic induction. Magnet vibrating in a uniform magnetic induction. Right? Let us consider a magnet north pole, south pole of the magnet, right, in an external magnetic field, right. Let's draw the external magnetic field in some other color. This is my external magnetic field. Right? So you have a magnet in an external magnetic field. Now, let's assume that the magnet makes an angle of theta with the external magnetic field. It is inclined at an angle of theta with the magnetic axis. This angle is theta, right? The external magnetic field is of induction B. The external magnetic field is of induction B. Now, if a magnet is placed in an external magnetic field, there will be two forces acting on the magnet. One on the north pole, the other on the south pole. The force that will act on north pole will be nothing but M into B. That's pole strength into external magnetic field. The force acting on the south pole will be in opposite direction and will be again M into B. Right? These are two forces equal in magnitude and opposite in direction acting at different points. Two forces equal in magnitude, opposite in direction acting at different points give rise to torque. That means when a magnet is kept in an external magnetic field, it will result in torque. Now let us find out the distance between the two. Let's consider a point, say P, right, such that Pn is perpendicular to Ps, right? Now, just let's write these assumptions down first. Consider a bar magnet. Consider a bar magnet, freely suspended bar magnet of magnetic dipole moment, of magnetic dipole moment M, suspended in a magnetic field. Suspended in a magnetic field of induction B. Right? Now, the magnet remains in equilibrium position with the axis parallel to the direction of B. If it is in this, if the magnet is released, see, initially I am keeping the axis of the magnet and the magnetic field parallel to each other, right? The magnet remains in equilibrium. The magnet remains in equilibrium position with its axis. Parallel to the direction of magnetic induction. Right? Now, if the magnet is released, there will be a small displacement of theta. If magnet is released, then there is a small displacement theta. If the magnet is released, there is going to be a small displacement theta. Right? Now, if it moves by an angle theta, that means it is going to move in a curved path. If it moves in a curved path, that means it performs an angular SHM, small displacement theta, and it performs an angular SHM. So the body is now going to perform an angular SHM, right? Now, when the magnet is displaced from its original position, the torque on it tends to bring it back to its original position. When the magnet is released from its original position, the torque will tend to bring it back to its original position, tend to bring it back to its original position. Fine. Now, if the torque is going to tend to bring it back to its original position, this torque has to have a magnitude of mb. This particular torque will have a magnitude of magnetic dipole moment multiplied by magnetic induction. I can say this torque will have a magnitude of mb, right? Now, in that mb sin theta, right? In which case, as theta is very small, therefore I can say that sin theta is approximately equal to theta. Therefore, the torque that will be acting, the torque that will try to bring the magnet back to its original position will be nothing but mb theta. Right? Do we get this clear? As theta increases in clockwise direction, torque will increase in anti-clockwise direction. As theta increases in clockwise direction, torque will increase in anti-clockwise direction. Right? Now, once you have this, I can therefore say that since they are increasing in opposite directions, T is equal to minus mb theta. Since torque and theta are in opposite direction, therefore I am going to put negative sign there. Now, if I is the moment of inertia, and d square theta upon dt square is the angular acceleration, in which case I can then say that torque we know is nothing but moment of inertia into acceleration, mi into angular acceleration. That means I can therefore say that torque minus mb theta is mi, moment of inertia is I, angular acceleration is d square theta upon dt square, right? In which case I can therefore say that d square theta upon dt square is minus mb upon I into theta, right? Out of which I can say m, b and I are constants, where magnetic dipole moment, external magnetic induction and moment of inertia are constants. Therefore, I can say that angular acceleration is directly proportional to angular acceleration.
So that should be dt square.
dt square. Angular acceleration is directly proportional to angular displacement theta, angular displacement theta, and is in a direction opposite to that of angular displacement. Angular displacement, right? Hence, I can say that a magnet freely suspended in an external magnetic field performs an angular SHM, right? Hence, the magnet performs angular SHM. Right? Now, if it performs an angular SHM, then I can say that the magnitude of the angular SHM, the magnitude of angular acceleration, the magnitude of angular acceleration is nothing but mb upon I theta, right? And where mb upon I is constant, which I can consider as the acceleration per unit angular displacement. Constant is always the given number per unit. Therefore, I can say where mb upon I is the angular acceleration per unit angular displacement, right? So, and we know that the time period t is given by the formula, 2 pi upon square root of, for an angular SHM it is given by the formula 2 pi upon angular acceleration per unit angular displacement. Therefore, I can say T is equal to 2 pi upon square root of mb upon I. Therefore, T is equal to 2 pi square root of I upon mb. That will be the time period for a magnet rotating in a magnetic field, right? In which case I can also find out the frequency. Frequency n will be nothing but 1 upon t. So frequency will be 1 upon 2 pi square root of mb upon I. Right? That will be the frequency of a magnet freely rotating in a magnetic field. This finishes the theory of this chapter. We'll stop this here for the day. Thank you very much.